So say we consider a rectangular cross sections, okay? And then, for example, if we know the pre-made, this is the center of the curvature. So we know that if that is a pre-made, for example, a section of the circular portion, so here is the known distance. So for example, let me call this is the R1, and the bottom here to here is R2. So if you protrude this one, basically this is the form of just like the circular section like this one. Okay. Don't laugh at me. I try to.
I'm not laughing at you.
You're laughing. You say
I thought of something funny.
Okay. So for this case, we see how can we implement that calculation. So R will be equal to, and let me give a dimension here. So for example, this is B, and this is the H. Okay. So R simply equal to A divided by R1 over dA. So this one, A equal to B times H. And for this one, this is the integral. And integration, you can see, we can do this one. The basically dA equal to 8 B times the, let me say, the dr. Okay, so this is B times dr. So here we can transform this into this. This is R, and dA comes into the B times dr, and R is to integrate from where to where? From the bottom to the top. Right? So that is from R2 to R1. I think. So from here that is B, H, and then we do the integration. B is constant, picking up here. So dr over R and R2, R1. So that is BH and B times the log R and R2 to R1, right? Something like this one. Okay, just show you how if that is regular, then we can implement that equation. And otherwise, and you can refer to we can refer to the next page here. Oops.
Your R1 and your R2
Yeah,
are just
so
switched.
why I reversed that one, I try to figure it out. Do you know why? It didn't tell the sequence, it didn't tell the direction of the integrations in the formula.
Because it could be from the distance C.
Because you're integrating from C the other way. From the top of the...
But from this equation, it didn't say anything. In this derivation, it didn't say anything about the
Oh wait, is there a... Is it because of the negative? It wouldn't be because of the negative, right?
I never think about this one before. Can I leave that to you? I move on and leave that to you for you to think about that one. And I would think about this one as well. Okay, so we keep thinking that one. But anyhow, just want to show you this is doable. And so for that case, we let me keep thinking.
Would it be because of the negative?
Shouldn't be. Let me keep thinking this one. So probably, I don't know. But anyhow, assuming if we do the homework, we just take up these formulas. Okay, so those ones provided to us, and then we can do the same. So R fixed. Then the next one, we're going to fix delta theta. So So now right now is, again, we look at the distribution of the green lines for the stress. We take the moment about the centroid. So this is the cross-section is in this viewpoint. We take the moment respect to this axis, and that should be equal to our given bending. And our given bending for this case using the value is m here. Okay. So we take the moment about the centroid. So that means here is, put into here is minus y times sigma x dA equal to 0. And again, this is on the whole cross-sectional area. And the same, this equation is the same as we did in for the uncurved beam. Okay, the same. So for this one, that derivation, we simply plug into this formulation to here and expand it. And let me give you the final result. And the final result basically will be leading to here. E delta theta, theta, and will be equal to RA minus 2RA plus and here I want to give you the definitions. Where the R bar represent is this is the R bar indicate the location of the centroid. This one is the locations of the neutral surface. And for the curved beam, in general, we can see the two quantities in general shouldn't be equal. Okay, so from the two equations here, the first thing you have to bear in mind, for the curved beam, the neutral surface in general won't pass the centroid. Before in our uncurved beam, we say that once we identify the centroid, the neutral axis passing to the centroid. You remember that one? Mm-hmm. Right? In our old story, for example, in our the straight beam, for example, we have the T-shape. You remember in the first step, we always is to calculate the location of the neutral surface. And the location of the centroid. Once we identify the centroid, say the neutral axis passing through. But not anymore for curved beam. The location of the neutral surface will above or below the centroid on the curved beam. So that means here into this calculation, you kind of bear that in mind. So that is the result. And let me rearrange this one. So this one is here, and then RA, basically this quantity can be related using this, can be using the this information here. Okay, so we can plug in this information to R here. So here we can rearrange the whole thing. Basically here the whole thing becomes like this. Sorry, this one is bending equal to n. So therefore, after we plug in this information and this information back to here, so we can have is this E times delta theta divided by theta equal to M A E. So here again, the E is the difference between the R minus R. Because the location of the centroid wouldn't be on the location of the neutral surface anymore, so they have the gap, they have a distance, and that is divided by E. So that E appears here. So from this equation, we solve for delta theta.
Where did you start out with the initial equation? Like, where did you get that?
This one?
Yes.
Yes. I'm expecting people to ask me.
Yeah, I was like, where'd you pull that?
So we look at here. So this is the cross sections. And let me take up the, for example, this is the distribution of the bending stress. This one is due to the bending like this. Okay, and this is the cross-sectional. Let me enlarge, this is a cross-section. Okay, so this is the neutral axis. So now we see this is the stress that we call the sigma x. The sigma x working onto the small area, and this is called the dA. The distance is from here to here is y. So sigma x multiply dA equal to the small force on this strip. That small force is acting to that direction. Small force multiplied with the distance y that give us the small torque, the small moment. Right? So we integrate this in this way, the moment is about this direction. Then we added up all the the moment under all the strips over the whole cross section. So that means we integrate this one. That is the summation of the internal moment contributed by A.
So that's M's effect, okay.
Okay.
Why isn't it negative?
Y is negative.
And that should be an M
And that should
too.
be
Oh.
So why is it not a negative over there?
That's using compressive force, so it would be negative. That would just be the same.
I think you are right. Because right now I'm here for this illustration I'm working on is on the magnitude. The rotation of the sense of the rotation has been taken care of. For sigma, for this case, because, okay, so here is a magnitude, here is a magnitude. Okay, but for the, in terms of sense, this one sigma, this one is compressive. So that means to make everything consistent, I need to add a minus here.
Okay.
Or otherwise we can try is this. We can utilize the small moment direction equal to R cross F, right? Right? Which one is the front?
I think it is R cross.
Yeah.
Yeah, it's R cross F.
Okay.
Why is it DM? I thought it was just
Okay.
M.
So the DM, so let me work on this one. So this is on the small screen, okay? So we can isolate. So for our DR, the R is the distance, which means is the Y, 0, 0, right?
Sure.
And for the small force,
X
and
is
that
the X
is go to the
direction, right?
negative X, so that is minus sigma X times dA. In this, because this is our X direction.
Mm-hmm.
So put into here, I think the minus sign will be automatically coming up here. So, okay.
And also corrects this one bottom half, one y will be negative. So this.
The negative, yes, the bottom portion is the same thing as the
So
bottom.
it'll
Yeah,
only be
the same.
positive.
Yeah.
I think the reason it's,
For example, if you look at the bottom one here, then basically the bottom one will become this one minus and this one positive.
Yeah.
Right?
So I think the reason before for the R1 and R2,
Hmm?
it's because you're going from the top to the bottom. So R1 is actually your minimum value. So you have to go
Excellent.
R1 and R2 first.
Can you say that again? Excellent.
Yeah, if you